The sin hz is analytic function. We have sin iz equals I times sin hz. Multiplying both sides of the equation by I, we obtain I times sin iz equals I square times sin hz. I square is replaced by minus 1 and we multiply this equation both sides by minus 1 and we obtain the final equation sin hz equals minus I times sin iz. Now we replace z by x plus iy and we multiply I inside the parenthesis. We can expand sin ix minus y using the equation of sin of a minus b equals sin a cos b minus cos a sin b. We obtain this step and after that we multiply minus I to each terms separately. We can replace sin ix by I sin hx and cos ix by cos hx. Now we have minus I when multiplied to I becomes minus of I square, which is positive 1. And this is the term involving I. Therefore, sin hx cos y is the real part and cos hx sin y is the imaginary part of sin hz. Since we have separated sin hz to real and imaginary parts, now we can evaluate the partial derivatives to check whether CR equations are satisfied here. We have u equals sin hx cos y and v equals cos hx sin y. Using the derivative formulas, d by dx of sin hx equals cos hx and d by dy of cos y equals minus sin y, we can evaluate respectively the partial derivatives dou u by dou x and dou u by dou y. Similarly, using the basic derivative formulas, d by dx of cos hx equals sin hx and d by dy of sin y equals cos y, we can evaluate the derivatives dou v by dou x and dou v by dou y respectively. We observe that ux equals vy and uy equals minus vx here. Thus, CR equations are satisfied everywhere in the complex plane and hence f of z equals sin hz is an entire function.